What I want to talk about this week is a slightly obscure but very useful and powerful C++ feature called Template Metaprogramming. And Template Metaprogramming was first made popular in this book, which came out about 20 years ago now, called Modern C++ Design by Andrei Alexandrescu. And what it shows us is how to use templates actually as a way of implementing algorithms rather than the more normal thing that we do of just generating types. And what got me onto thinking about showing you this was actually a video I watched on another YouTube channel, a channel called Numberphile, which is absolutely fascinating if you're into mathematics and want to see about all sorts of areas of maths. But what they were mentioning in this video was what's known as the Collatz conjecture. The Collatz conjecture is based on a sequence of numbers known as 3x plus 1 numbers. And 3x plus 1 numbers follow a very simple sequence that you start with a seed number. So let's start, for example, with the number 6. And then you follow a very, very simple rule. If your number is an even number, you halve it. If it is an odd number, then you calculate the next number in the sequence by tripling it and adding 1. So that's the 3x plus 1. So if we start with our 6, it's even, so we halve it. That gives us 3. 3 is odd, and so we do the 3x plus 1. So triplet plus 1 is going to give us 10. 10 is even, so we halve it. 5 is odd, so 3x plus 1 is 16. 16 is even, so we halve it, that gives us 8. 8 is even, so we halve it, that gives us 4. 4 gives us 2. 2 gives us 1. And when we reach 1, we actually generally terminate this, because although we could carry on, we don't get very far. Because if you think, well, 1 is odd, so 3x plus 1 gives us 4. 4 we halve it, gives us 2. 2 gives us 1. And so at the end, we just end up with this very, very tight cycle. And so that's the sequence of 3x plus 1 numbers. And for different numbers, you will get various different sequences. But what the Collatz conjecture is that whatever number you start with, eventually you will get down to 1. And it's one of these conjectures in mathematics that everybody believes is true, has been tested out for millions, billions of numbers, but for which there is no proof. Now, I'm not going to be doing anything to attempt to prove it or disprove it, anything like that. I'm just going to be having a look at the programming we can do in order to implement and calculate this sequence. So I'll start out actually in C#, because in C#, it is really, really simple because we can use what I was talking about quite a few videos back, the idea of yield return for putting together a sequence. So let's start that. What I'll do here is I will put in a public static I enumerable, and here I'm going to make this an I enumerable of a tuple with a uint, an unsigned int, just so I can get really big numbers in here, that I'm going to call count. So that's going to be the index of the item in the sequence. And then I'm also going to have a uint that I'll call value, and that's going to be the actual value of the item. And so we'll call this just Collatz. And then I'm going to kick this off with our seed value. So that would have been 6 in the example I just gave. And then it's all pretty simple, because what we can do is say uint count equals 1. And then the first element in the sequence is going to be the seed itself. So we can simply say yield return count comma seed. And then we'll say while seed is greater than 1, because as we discussed, we're going to terminate at 1. Then we'll have if seed %2 equals 0. So that's the test for evenness. And if it's even, remember, we're going to say seed divided equals 2. Otherwise, seed equals 3 times seed plus 1. So that's our 3x plus 1. And then finally, we can say yield return, and we're going to say plus plus count. So we increment the number and then just return the seed. And then in my main, all I can do there is we'll do a for each, and then var val in Collatz, and let's do it with 6 like I had for that example. And then we'll do a console write of val dot count colon val dot value. And then just so we can step through it to start with, I'll do a console dot read line, so we just have a slight pause between each one. And let's run that up. And so we can see we start with 6, that's element number 1. Then we've got a 3, so that's halved it. Then we've got 10, so that's 3x plus 1. Then we've got 5. Then we've got 3x plus 1 again, 16. Then 8, then 4, then 2, then 1. And at that point it terminates because we put that terminator in there. And so if we just get rid of that read line now, and then we can see that nice and neatly. And then we can throw in some other values. So let's just copy and paste that. And let's try it with 10. Line break in there. And so we can see that with the 10, well, actually, something interesting's happened there because 10 already features in our 6 sequence. Then actually, once we get to that point, it's guaranteed to be exactly the same because it's just following the rules we've got there. If we tried it with something maybe a bit more interesting, let's try 100. Then we can see actually 100 is quite a complicated one. There's 26 steps in the 100, but we can see eventually it has to home in on that 16, 8, 4, 2, 1, or it has to if the collapse conjecture is true, which we don't know. If we went for something like, say, let's go for 1,100, then actually we can see the 1,000 is quite a long one. That takes 112 iterations, whereas 100 takes only 26. But it's pretty much randomly distributed. And in fact, what people tend to be most interested in is not necessarily the actual sequence, but what that count is. Because obviously, if you ever got a number for which that count was infinite, effectively, then you'd have disproved the collapse conjecture. Now, actually, what I'm doing there isn't particularly efficient because it doesn't take account of this fact that there's a lot of duplication. So if we take that back to what we had a while ago, when we had our 6 and 10, we said that once you hit the 10, it's exactly the same, but actually I'm doing all the calculation again. So I can do a rather more efficient version of this, and I'll put that in the solution I put on GitHub. And if I've got time, I might actually show another video with the explanation of how all that works. But what I was going to show you is how we can actually use this idea of template metaprogramming in C++ to get that to work. So what I'm going to go over here is now to this C++ application. Now, just a very quick review of templates. The classic way that we do templates in C++, similar to generics. So I would say template as the keyword, and then I say type name T for the generic type I want to have, the template type I want to have. And then I might say something like class collection. And then in here, let's give it a private section, and then just say T star values. And although there's lots more to do there, that's the basic way of putting it together. And that's very similar to what we have with generics in C#. However, to get this idea of template metaprogramming working, we've got to actually exploit a couple of additional features we get in C++, templates that aren't really available in generics. And one of them is that we can have as a template parameter any integral data type. So I could, in here, also maybe have that int size. And that would be useful if I was going to have a fixed length array. And then we could just say something like t values size. And so we've got a fixed size array. And to use that, I could have written something like collection double 10. And that would be my fixed size collection of 10 elements. The second neat feature we get with C++ templates is what is known as partial specialization. Because if I were to, instead of having a collection of doubles, have a collection of bools, you might realize you're going to encounter memory layout problems because a bool can actually be stored as a single bit, and it might be very inefficient if you stored your collection the same way as doubles. So what we can actually do here is this. We say template and then just the one generic parameter, int size. And then I say class collection. And then I specify the one parameter, bool, and then just use that size for the other. And so what now happens is, if I put two instantiations in here, so we'll have one for doubles that we'll call col1 and one for bools that we'll call col2. And the one for doubles, it just uses the general purpose template, so we get that one there. Whereas the one for bools, it spots that we've got this specialization and it makes use of that. Just to prove that, actually, let's just change that to public, and then also in here, put in public and then just call that int x, just really as a marker. And then you'll see what I can do here is if I type col1 dot, then it's got values, whereas if I type col2 dot, then it's got x. So you can see that the compiler has chosen between those two, and we've got that partial specialization. And those are the two tricks we need to do this template metaprogramming. First one of these I'm going to show you is actually rather simpler than the colac sequence. I'm just going to show you a way of calculating factorials using this template metaprogramming approach. Kind of unnecessary, but we can see how it's going to work. So what I'm going to do is I'm going to put in here a template. Again, I'm going to do an unsigned, and I'm going to call this just n. And then I'm going to say struct. I want it to be a struct just because I want everything to be public, so that's easier than putting the keyword public in. And then we're going to say factorial. And then in here, I say static const. So it wants to be static const, so it's most definitely a member of the class. We don't deal with any objects when we're doing template metaprogramming. So that's what we've got there. Then unsigned. And then value. And I'm going to say value equals n times, and then this is the neat bit, we say factorial instantiated for n minus 1, and then put in the value in there. Okay, so remember that's how factorial works. So factorial of 6 is 6 times 5 times 4 times 3 times 2 times 1, but that is basically 6 times factorial 5. Factorial 5 is 5 times factorial 4. So we can do it in this recursive way. We've only got one problem there, though, of course. It won't terminate. So when we get down to n equals 1, it's going to then give us factorial of 0, then factorial 0, try and give us factorial of minus 1. Doesn't work. And that's where the partial, in fact, in this case, complete specialization comes in, because I'm going to say template, and then we've removed all of them. So I just put empty brackets in there, and then I'll nick all of this. But then what I'm going to say this is factorial instantiated for a value of 1. And of course, we know that the factorial of 1 is 1. So I can simply put the 1 straight in there, and that will act as the terminator. Because once again, if I ask for factorial 6 or factorial 5 or whatever, it will use the general form. But as soon as here we ask for factorial 1, it will just give us back that termination. So let's get rid of that. And now let's just in here do a cout, and then factorial 5 equals, and then we instantiate the template for a value of 5, colon, value, and then just pop end on the end. And then I'm just going to change the startup project there. And run that up, see what happens. And there you can see it's 120. So 5 times 4 is 20, times 3 is 60, times 2 is 120. So that's worked correctly. But the important thing about these things is the calculation is entirely done by the compiler. No calculation is being done at runtime whatsoever. And in fact, we could do something like const expression, and then unsigned fact5 equals, and then just put the factorial 5 in there. And then because const expressions have to be known at compile time, it's absolutely clear that's being calculated by the compiler. The one slight problem with this is factorials explode pretty quickly. So if I were to try and do something like factorial of, say, 300, then we get a couple of problems. One is we go beyond the range that we can fit into an unsigned, and also we potentially go beyond the stack depth. Certainly if I went up to say something like 3000, then you can see we actually get a compile time error saying that it can't compile it because the stack has gone too far. So not very practical for this sort of thing, but actually when it comes to these collapse sequences, they don't get anything like as big as quickly as factorials do. So let's put that one together then. So we've got our factorial, but what I'm going to do now is a more complicated one for this 3x plus 1 sequence. So what I will do is, firstly, I'm going to declare a template, and then it's going to be an unsigned int that I'll call seed. And then again, we'll have a struct that I'll call collapse. And then that of itself isn't really going to do anything because I'm also going to have a template that takes more parameters. It's going to have an unsigned depth, an unsigned seed, and also a bool, which I'm going to call odd. Bool is an integral type. I mean, it's effectively either 0 or 1, so that's what we've got there. And this I'm going to call struct collapse base. And then my collapse, the only way with template metaprogramming that you can effectively call something else is to make a template instantiation. So I'm going to say colon public, and then this thing I've called collapse base. And I'm going to instantiate it with a depth of 1, with a seed of seed, and then with an odd of seed %2. Because remember, that's going to give us 0 for even, which is in fact false. So that's why I've put that in as odd. But you can see actually what I'm doing there in a very, very different way is really the same I had before with the C# version. Because remember what we've got here, there we set the count to 1. Well, that's what I've called the initial depth as 1. There we had the seed. And then there we have the test for whether it's odd or even. But of course, that test is being done while the program's running, whereas this test is going to be done by the compiler. And that's where we need to do our partial specialization, because what I'm then going to do is have different partial specializations of collapse base depending on whether we've got even or odd, and that the compiler can work out. So again, let's start out by copying that. And then this one is going to be the odd version. So we will take the odd off there and then instantiate this for depth, comma, seed. And then, because this is odd, we're going to hard code that as true. And then again, I'm going to do the trick of using a base class. So here, I'm going to say colon public, collapse base, and I'm going to pass in depth plus 1, because we've gone one further down. Because this, remember, is the odd version, I'm going to pass in seed times 3 plus 1, because remember, that's what we're doing, it's odd. And then I need to pass in whether seed times 3 plus 1 itself is odd or even. So I'll take all of that and do the %2 on that. So that's going to call, as a base class, another iteration, but it's going to be for the odd version. Then if we do another one, so this time we set that to false, and then we're going to do seed divided by 2, because that's what we do with even numbers. And again, there we'll have seed divided by 2. And then lastly, just like we had with the factorials, we've got to terminate this. So one last one of these we're going to have. And in this case, we're not going to make the seed a generic. We're going to put in a hard-coded value of 1 in there. And in this case, this is our terminator, so we don't go any further. We do the same sort of thing as we had with the factorial. So we've got static, const, unsigned, and then we'll say count equals depth. Because remember, what we're trying to work out here is we're not trying to display the entire sequence, we're just trying to work out the size of every sequence. And so because every step we've taken down, we've increased the depth by 1, when we get to the terminator, which we've got here, then we just say count equals depth. But what that now means is, here I can do a cout, and then if I do a collapse of, and let's do the example we had before, of 6 equals, and then we're going to say collapse instantiated for 6. So that's going to instantiate this thing, which is going to instantiate that collapse base, which is then going to instantiate another one and another one. And in the end, we should just need to have the count there. And let's run that. And we can actually see it's failing, and it's failing basically, you can see on this huge stack dump, because it's not terminating. And the mistake I made, easy one to do, notice I put that terminator for a value of 1 and false. But of course that false is the odd or even. And so whenever we call 1, that's actually going to be true. So we've got to change that to true. You've got to be careful about these things. And so if we run that, we get that the depth of the collapse for 6 is 9. If we just go back to our multiple startup, and then if we in here go back to, we've got the one for 6 there, let's just get rid of that one. So if we run both of those up, we can see that we did have 9 elements and we get the result of 9 there. If we just change those a little, so let's put that bigger one of there, 100, and then 100 in here, and run them both up. So there we've got the 26 steps it takes for the 100, and there we've simply got the result of 26. Or if we even go a bit further than that, go for 1,000, and run that up, we've got 112 steps there, and 112 there. But remember, all that C++ calculation was done entirely by the compiler, whereas in C#, it's doing it at runtime. So that's just a quick look at some of the ideas behind template metaprogramming in C++. And using this example of the 3x+1 sequence, we saw how we could do the same sort of thing, not exactly the same, in both C# and C++. But at C# it was the program doing the work when it ran, whereas in C++ it was all done in advance by the compiler. So I hope you enjoyed that. Hope it made sense. Do subscribe, do ask me questions, and I'll see you next time.